Okay, then what did I say? I said we need to increase the P to be able to push the Kalman filter to and go and explore more options to be able to track the change and quantify the level of the damage. And as I said, so far in my Kalman filter, I'm going to write it here. So far, I was assuming Q and R are fixed, but in reality, they are not. And there are many techniques in the literature you can go and look into, and that people are using to be able to use adaptive techniques for Q and R modeling and measurement uncertainty. But in this presentation, I'm going to talk about two of them. The first one is forgetting factor technique. And what is that? It says in every iteration, Q at step k plus 1 is alpha qk plus 1 minus alpha Kalman gain y minus y hat. Let me do it like this. Kalman gain y minus y hat transpose. Which this y minus y hat is your innovation term. Difference between the model prediction versus measurement. And r k plus 1 is alpha r k plus 1 minus alpha y minus y hat in each iteration, y minus y hat transpose plus p y y. My point here is to show you that we using the forgetting factor we define a hyperparameter alpha and take a portion of this alpha. It could be different for, I call it alpha q and alpha r, and both alpha q and alpha r are between 0 and 1. My point here is to mention that we define a hyperparameter and get a portion of the modeling error or measurement error from the previous step and look into the current step innovation term and Kalman gain or the covariance of the predicted measurement to calculate the new Q and R. Once you have a change in your model prediction versus the actual measurement, these terms increases. You see, then if you give a big weight to the current state term, these Q and R get increase and increase your p-value here. That's the main point. Then if you want to quantify the level of the damage in your system, it's better to use a adaptive Q and R or assume Q and R are changing over time in each iteration. And because we have the innovation term here in the forgetting factor technique, what's happened once you have a change, this Q and R will increase and eventually increase the p-value and push the Kalman filter and give Kalman filter more fuel to go forward and explore more and quantify the level of damage. The second technique I'm going to introduce is window-based. I call it window-based. Adaptive technique. And what it says for example, let me try with another color. Q at time k plus 1 is equal to 1 over a window of length of window Q summation of I equal to 0 to WQ. It is Kalman gain y minus y hat Kalman gain y minus y hat transpose. And we have the same thing for r k plus 1, which is 1 of window R summation of y equal to 0 window R y minus y hat y minus y transpose plus p y. Okay. What it means? It means for this technique, you look at you choose a window and you look at the predictions and the innovation in a specific window, and try to, and in each iteration, you take the history of the signal from the specific up to a specific time step and calculate Q and R for that the time step based on the previous prediction and sensor data and considering the window you choose. Then, and again, if you have a change, you are able, you have the y minus y hat for each iteration, and which you keep the history, and it increases the Q and R, increases the P, and helps you to quantify the level of the damage. Now, I'm going to show you the results for the three-story building we were talking about and see that, and compare the robustness of these two techniques I introduced, window-based and forgetting factor-based technique. Okay, here in this slide, I'm gonna compare the robustness of these two adaptive techniques I just introduced for unscented Kalman filter to quantify the level of the change for this three-story building. And the story is like this. The white line for both parameters and states shows the ground truth, and the purple or other colors you see here are the estimated values for states and parameters. For example, for the stiffness value, the initial stiffness value is 50K, and at time 20, we change it to 45. And for damping value, we increase the damping value from 300 to 350 here. And the first column is the results for forgetting factor-based method, and the second column is for window-based technique. As you see here, the forgetting factor-based method is quite fast, you see, at the beginning to catch the ground truth for both stiffness and damping value. But and window-based method is a bit lazy, and you see at the beginning there is no change, which is based on the window size you choose for your technique you're using. And once you have it, the interesting part is here. We impose the damage at time 20 for the both cases. And as you see here, forgetting factor-based technique is a bit lazy to catch to quantify the level of the change for stiffness value. And for damping value, is not able to quantify the level of damage. But window-based technique, on the other hand, is although it is slow at the beginning to catch the ground truth, but for damage is quite fast. Then what we conclude here is that if you have a system that you just want to do a real-time system identification problem, and there is not that much change happening in the system, and the forgetting factor technique is the right choice for you if you have a gradual change or the parameters are not changing over time. But if you have a quick change or damage happening in the system and you are aware of that such a thing might happen for your system, window-based technique is a better choice for you to go forward with and quantify the level of the damage. Okay, then so far in this video, I talked about the two different adaptive techniques to be used along in the unscented Kalman filter algorithm to quantify the level of the damage. But for both of these two algorithms, what we did, we brought some new hyperparameters. For example, forgetting factor. Or for forgetting factor techniques, we have alpha R and alpha Q, which we need to find the optimal value for that. And for window-based techniques, we have window size. These are new hyperparameters, and they need tuning, which we need to find a solution for, because it takes sometimes for complicated problems, it takes time to find the optimal value, and usually people do some try and error to find the best value or optimal value for these hyperparameters. In the next video, I'm going to talk about the hyperparameter tuning for unscented Kalman filter. Either you want to use a constant RNQ or adaptive RNQ the techniques. Then thank you very much. Then in the future video, we will talk about how to find, how to optimize or find or tune the unscented Kalman filter for different tasks we have in mind. Thank you.